All right, we're up and moving again. So power is how quickly work is done. Power that's all power is. It's how quick we can get work done. All right. So power is work, the amount of work, the energy we're expending, the chemical, the physical work that we're doing, the energy that we're divided by the time. Okay. So remember, work is equal to force times distance. So power is force work force times divided by time. Now, what my boss did here, former boss, he's South Dakota State's big boss now, but anyway, force, we've got S divided by T. What's distance divided by time? Well, that's a speed. So we could also say that, but distance is speed or velocity. So we could say that the power is the force times the speed. We went to power is measured in watts, just like light bulbs. Okay, in fact, that's electrical energy that we talk about, and that's measured in joules. And so it's putting out like a 100-watt light bulb is putting out 100 joules of energy per second. Okay. Rock climbing output. Me personally, I would have done this completely different than what you're about to see. Okay. He did that climb in 4 minutes and 25 seconds. So power is force times speed, which is fine, or just the work divided by the time. That'll. In fact, I want to do it that way. We'll walk through the force times speed thing, but let's do the work divided by the time. All right, let me write down what we have here. We've got 65 kilogram rock climber. Okay, so that's the mass. I'm writing this down. So, and the time is 4 minutes 25 seconds. What's the unit that we use for measuring time? Do we use minutes? No, we use seconds. So we got to convert the whole thing to seconds. So the power. All right, so there we go. And he went, the height that he went was 136.4 meters. All right, first of all, you might be asked the question, the power question could go so screwy as to say, hey, 400 feet, 400 feet in meters. Google, help me out here. Help a brother out. Whoa, that's 121.92. Wow, that's not the 136.4. I wouldn't believe this slide at all. 400 feet? Climbed around 400 feet. Oh, I see. The actual video said it was 136.4 meters. So let's find out how many feet it actually was then. So let's go the other way. Let's go 4 meters into feet. Yeah, it's about 447. It's actually about 447 feet. So we'll stick with 136.4 meters because that's what's on there. All right, now this is the way I like to do this problem. I like to go, okay, so we'll take m times g times h, which is the work that he did. Get up there. Let's go ahead and get that number. 65 times 9.8 times 136.5. And we've got 8599.5. And that is newtons. So work done by there. And oh, times that. No, that's joules. That's joules. What? Oh, I forgot the 6. I was like, wait a minute, I'm off by a factor here. That makes no sense. Slow down. What time is it? It's only 3 o'clock. The traffic doesn't get bad for another 45 minutes. I can slow down. Except I'm getting thirsty. Got cold bear in the front now. Anyway, so don't want to encourage that with students. All right, 65 times 9.8 times 136.5. 86,950. 5 joules divided by, now the time would be 4 minutes, 25 seconds, which is actually 4 times 60, 240 seconds, because there's 60 seconds in a minute, plus 25 seconds. It's equal to 265 seconds. Joules per second gives me the time. See, I didn't like doing the velocity thing. I don't know why we did that slide that way. And I don't know why I say this every year. So I take the answer divided by 265. Boom. 328 watts. Same energy as three and a quarter 100-watt light bulbs. Okay, well, let's at least go back and get closure with it. 0.51 meters per second. That's his rate going up. You know, half a meter per second. Not very fast. I mean, I can definitely walk faster than that, but I'm not going up a vertical hill. The power, 328 watts. So it all worked out the same. The power of sitting. Now you can just sit there. You've got your internal heat that's causing all kinds of power. Okay, you've got your internal heat. So if you're just sitting there, there are probably 63,000 seats here in the University of Phoenix Stadium. Is it still University of Phoenix Stadium? I thought they went completely tits up once the military said, hey, we're not going to give you, we're not going to pay 90% of our troops' tuition to your school anymore, but I'm not sure. All right, anyway, so that's 66 megawatts of heat. This is so 63 times 100, so that's 6,300,000 joules of heat every second. So a light bulb is like 100 joules of heat every second being put. So that's 6 million joules of heat being put out every second. A power plant, on the other hand, is and so that's like 6.3 megawatts, right? Because mega is a million, right? So that would be about 6.3 megawatts, whereas a small electric plant puts out 1,000 megawatts. So a stadium, you take 1,000 divided by 6, it's about 166 stadiums of people will produce as much power as this power plant. But what they sell you is energy, because a kilowatt hour, for those of you who pay your bills, pay the bills, know that it's in kilowatt energy. So anyway, so you got the Back to the Future. I think I put the gigawatt. Well, it'll come out terrible because I've got it on here. Hopefully it won't come up. So the DeLorean has 1.21 gigawatts or gigawatts. They said it wrong because back in 1985 when that movie was made, when I was all of 25 years old, okay, back when that movie was made, in fact, I saw it on Okinawa the first time. It came out in about 86 and finally got out to the theater on Okinawa when I was a young lieutenant. But anyway, the gigawatts, he called it gigawatts because that just sounds funnier. But we didn't have computers that had gigs back then. We didn't even have computers, really. I mean, you look at old TV shows from the mid-'80s, there's no computers on desks. Nobody has a computer. The secretarial pool and the administrative assistant people, they have fancy typewriters, but nobody has a computer, really. I mean, there's a big computer somewhere where you have to hang tapes on it and stuff like that. That's less powerful than this little iMac. Okay, I'm going on and on. All right. Oh, and we'll do the power conversion. We'll do that last. All right, so we're about done with this little mini lesson.